Today, Taylor's theorem. Yeah, in this class, we often use Taylor's theorem. This topic is from section 1.1 in the first book on my notes or on the syllabus. Before I present Taylor's theorem, let me introduce a notation first. Let C and AB is notation. C means continuous. AB is an open interval. Let this notation below the set of all functions f for which function f and derivative, second derivative, and so on, until derivative of order n, take derivative n times. For which all these functions are continuous. Everywhere on the open interval. AB. Yeah. So put all the functions, all these functions together, we have a set, the set allocated to this. C means continuous and derivative of up to order n. A, B, open intervals. Now with this notation, I can present Taylor's theorem. Okay. Okay. Taylor's theorem. Taylor's theorem. Suppose function n from this set. If function n from this set, okay, n plus 1, okay, derivative up to order n plus 1. This symbol means f is in this set or from this set. Then for any 2 points, x and c, from the open interval AB, in the open interval AB, okay, we have f of x, function value f x is equal to function value as c plus 1 over 1 factorial derivative as c, x minus c. Derivative as c is assumed to exist because the function is from set, the function has derivative of order up to n plus 1. And then plus 1 over 2 factorial second derivative as c, x minus c squared. And then plus, okay, plus. Yeah. 1 over n factorial derivative of order n, then x minus. The left side of this equation is a general function. The right side is a polynomial. To make the equation true, we need to add error term. Okay, error term. Pass error term. Name the error term En of x. How to compute the error term here? Where the error is 1 over n plus 1 factorial times derivative on function n plus 1 times, and then evaluate at some point psi times x minus n plus 1. Okay, where the point psi. In general, we don't know the point psi. We just know this point depends on c, depends on x, and also between c and x. Where psi is a point between c and x. In general, we don't know the point psi. We just know between c and yeah. This is a Taylor's theorem. Taylor's theorem in Lagrange form. Taylor's theorem has several forms. This is Taylor's theorem in Lagrange form. We often use. Two special cases about this equation. Yeah. These two special cases we often use. Two special cases. Special cases. The first case is C is 0. The point C is 0. Then when C is 0, this equation can be simplified into the following equation. F x is function as 0 plus 1 over 1 factorial derivative as 0. Right? C is 0. Then x minus c is x, just x. And then plus 1 over 2 factorial second derivative as 0. Then x squared. Yeah. And then plus down, then plus and factorial derivative of order n as 0, then times x to n. Then plus error term. Error term. Okay, where error term is c is 0. Okay, so 1 over n plus 1 factorial sine x n plus 1. Okay. The point sine, usually we don't know. We just know okay, where sine is a point between 0 and x. Yeah, just first case we often use. Now, second case. Second case. Yeah, the ball is too small. You know? I want to keep this and erase. Okay, now can I erase this part now? Okay, yeah. Second case. In this equation, x and c, any 2 points. Okay, now second case. Replace x in the equation by x plus h, and the c in the equation by x. Then we have the following equation again. The x, replace x by x plus h, c by x. Then we have f x plus h is equal to f of x plus x. Right? Now, x minus c. X now is x plus h. C is x. So this is h. And then plus 1/2 vectorial. Second is then h squared. X minus c is h. And then plus 1/n vectorial f derivative n times of function f. Then you get x h n. Yeah. Now plus l plus l, where the l is, yeah, l is still by 1/n plus 1 vectorial derivative of function n, n plus 1 times evaluate at some point sum. Then x minus c is h. So h to n plus 1. H to n. Now the point psi. Psi is a point between x and x plus h. We often use these two special cases. Now next, let me show you one example about Theorem's field. So let's take a look at this example. Consider this function. And the interval in Taylor's theorem AB be level 1, 1. Okay. The point C is 0. Okay. Just consider this case. Now, by Taylor's theorem, expand this function into polynomials. Okay. Okay. Expand this function in to Taylor's series. Taylor series. This sum is a series. This special sum is Taylor's series. Yeah. A sum. Sometimes some people call it a series. Yeah. Infinite series, a sum of infinite many terms. Finite series, a sum of finite terms. Yeah. Now, let me expand. So, we need derivatives. So, let me compare derivatives by quotient rule. It's easy to see derivative on this function k times is equal to -1 to k times k factorial over 1 plus x k plus 1. Then I need to evaluate derivative at point C. Now C is 0. So derivative k times at 0, right? We need 0. Derivative at C. Now C is 0. Now plug in 0 in x. Left is 1 k times k factorial over 1 plus 0 k plus 1. So denominator is 1. So numerator is -1 k times k. Okay, now let me plug in derivative into the equation. Okay, so therefore we have let me erase it. Therefore we have function f, yeah, this special function is equal to 1 plus -1 times x. Yeah, just a plug-in derivative, and then cancel out the factorial, k factorial. Then you get -1 squared times x squared plus -1 n times xn. Then plus error 10 plus error 10. Yeah, error 10. Yeah, plus error. So where the error term, yeah, is 1 over n plus 1 factorial. Now, derivative n plus 1 times. Yeah, n plus 1 times. Then it is -1 n plus 1 n plus 1 factorial, right? Here. K is n plus 1. So -1 n plus 1 times n plus 1 factorial. Then the bottom is 1 plus x. Now x is, yeah, I am talking about this guy. Yeah, this guy. Yeah. So x now is sine. So 1 plus sine. K is n plus 1. So n plus 4. Yeah. Then times x minus c. C now is 0. So times x n plus 1. Yeah. Now sine is a point between C. C is 0, between 0 and x. Now I can do it. Cancel out n plus 1 factorial. Yeah. Then we have negative 1 n plus 1 over 1 plus sine n plus 2 times x n plus 1. Where sine is a point between 0 and x. This example has two parts. First part, expand the function into Taylor's series. Done. Yeah. This is a Taylor's series plus error. Error is given by given. Now, second question. Number 2, how to answer this question? How many terms in the series? Yeah, series. Yeah, is sum. Okay. Sum. Okay. Up to this term, not including the error. Okay. How many terms in the series need to be used to approximate the function value and negative 2. Okay, function value and negative 2. What is that? 1 minus 1 plus x. So this is a 5 over 4. With accuracy of 10 to negative 8. Actually, this question is asking how to choose n so that the error is less than 10 to negative 8. Okay. What is n? N is the number of the terms in the series. How to choose n so that error less than 10 to negative 8. And now error is here. Let me solve. Let me answer. We want error in absolute value. And error given here, negative 1 n plus 1. 1 plus sine n plus 2. Yeah, this is the error. Times x n plus 1. Absolute value. Yeah, we want less than 10 to 8. How to find n so that this inequality is true? Now let me simplify. Okay, sine. We don't know what is sine, but we know sine between 0 and x. Yeah, we know. Okay, we know. We know sine between 0 and x. Now, what is x? X is a negative contour. Okay, yeah. Now x is negative contour. Yeah, x negative contour. So, negative contour less than sign, less than 0, right? Between. Okay. Now, I can estimate 1 plus sign from these inequalities. The signs of 1 plus sign, let me add 1 to the three terms. So 1 plus negative contour on 8, then 1 plus, right? Sign less than 1. Okay. So therefore, the error, okay, error. So, okay, so the error, actually, x is negative contour. The error is take absolute value. This guy is absolute value, just 1. So it is 1 over 1 plus sine m plus 2. Okay. X is 0.2, so negative 0.2, absolute value actually times 0.2 m plus 2. X is negative 0.2, then take absolute value, answer 0.2. Okay, now denominator greater than 0.8, less than 0.1, so is less than 1. 1 over 0.8 m plus 2 times 0.2 m plus 1. Okay? Yeah. Key step here. Okay? Yeah. 1 plus sign between 0.8 and 1. So 1 over less than. And error less than this number. So in order for the error, original error less than 10 to negative 8, I just need to find n. So that this number less than 10 to negative 8. When this less than 10 to negative 8, then the original error less than 10 to negative 8. Now, I solve this inequality for n. If this is true, then this must be true. Solve this for n. Okay. Point 2 n plus 1 over point 8 n plus 2 less than 10 to negative 8. Yeah. How to solve this inequality for n? And the bottom has n plus 2, so many 0.8. So how about maybe move 1.8 to the left side? Yeah. n plus 1. Move 1.8 to the right side. Times. Right. Then this is what? 0.2 over 0.8 n plus 1 less than 0.8 times 10 to the negative 10. Take log, lateral log on the both sides. Then lateral log. Take lateral log on the both sides. Yeah, lateral log. Lateral log brings down the power. So n plus 1 times lateral log 0.2 over 0.8 less than lateral log 0.8 times calculator. Let me see, do I calculator, you get this is a negative number. Negative number. And also this is a negative number. Negative. Now I move this number to the right side. When we move a negative number to the right side, change the direction of the inequality. Okay. Yeah. Okay. So here, n plus 1. Okay. Change inequality direction. So at 0.8 times n to negative 8. Then over 0.2, 0.8. Yeah. Yeah. Solve this equation for n. Now move 1 to the right side. So minus 1. Then calculator. This number is 12.4486. That means that how many terms will lead so that the error is less than 10 to negative 8? 30 terms in the Taylor series. Yeah. So the answer is, conclusion is 30 terms in the Taylor series to be used to approximate this function value with error with accuracy of 10 to 11. This is the conclusion. Taylor's theorem has several forms. This form is Taylor's theorem with error in Lagrange form. Now the next form is Taylor's theorem with error in integral form. Okay, integral form. Taylor's theorem in integral form. Okay. Again, we assume the function from this set. T and X in the open interval. We have the function f can be approximated by a polynomial of this form. Of course, we need to pass error. Left side is a general function, right side is polynomial. To make them equal, we need error. The error now is in the form of an interval, where error is 1 over n factorial times integral c to x function n plus 1. Yeah, this is a take derivative from function f n plus 1 times then evaluate at t times x minus t and dt. This form of error is called Taylor's theorem in integral form. The third form. So far, we only consider one independent variable, x. How about if the function has more than one independent variable? Then what is the corresponding Taylor's theorem? Okay. Yeah. The next Taylor's theorem is set two variables first. Two variables first. Now it's time. Is open interval just for x. Now we have x and y, two independent variables. Change this interval into a rectangle, okay, in the xy plane. Okay. Then omega b a b is open interval cos cd is open interval. The rectangle in R2 two-dimensional space. It's hard, huh? You don't think so? Yeah. But anyway, yeah, let me plot this rectangle. Yeah. X, Y. Okay, X and Y independent variables. Interval AB, say A, B on X axis, CD on Y axis. Yeah, CD on Y axis. Now, this rotation means is rectangle. Yeah. because open intervals, they don't include endpoints. So the boundary not include this rectangle. Omega means this rectangle doesn't include the boundary. Let omega be that rectangle, and let function f from this step, okay, C continues. N plus 1 derivative of order n plus 1, okay, derivative. Now, the function has two independent variables. Derivative are partial derivatives. Take derivative, say on x n plus 1 times, or derivative on x n times of y 1 times. Okay. Yeah. But all the derivatives will require to be continuous. Yeah, continuous on the rectangle. Okay. Now, conclusion. Okay. If x, y, and x plus h, y plus k be 2 points in omega. Yeah. In omega, in the rectangle, pick 2 points. Yeah. Okay. Yeah. Okay. 1 point. This is x, 1. Second point. Yeah, second point. This is x plus h, y plus k. Okay, second point. Then function value at this point can be expanded into polynomials. This time I use sigma location for sum. Okay, summation. I still to n. I is integer start with 0 and ending at n. Okay. Then I factorial times h partial derivative partial x plus k partial y. Then power and I. Okay. Yeah. I will in a moment I will explain what this notation means. Okay. Apply to fx. This is yeah, the right side polynomial in h and k. In h and k. Polynomial in h and k. Left side is a general function in h and k. Consider x, y visit in this equation. X and y, consider them constant. H and k variables. To make general function and polynomial equal, we need to add error term. Error term, yeah. Depends on h. X and y here, constant. Then the formula for the error, we have E and HK. is 1 over n plus 1 factorial h partial x k partial y. Then the power is n plus 1. I don't have sufficient. I don't have enough space. Okay, let me do it. Yeah. The error is n plus 1 h partial x k partial y. Then the power n plus 1. Then n x 1. I will explain what this means. After compute this, then plug in this point. Okay, yeah. X plus theta h, y plus theta k. What is theta? Where theta is some point between 0. Yeah, this theta just now, the sign, the point sign in Taylor's theorem with a single variable. Yeah. We don't know what is sign. Okay. Yeah. What is theta? Okay. We don't know what is theta. We just know there is a point. This point depends on many things. Depends on x, depends on y, depends on h, depends on k, and also depends on the function. Yeah, this point. We only know this one between 0 and 1. There must be such a point. So then this equation is true. I don't have time, okay? Then let me repeat this Taylor's theorem Wednesday, and I explain what this rotation is. Okay, then yeah, I finished today's class here. Then see you Wednesday.